Okay, hello everyone. So, welcome to another class of gravitation. Yeah, it's me again. Okay, so in the previous classes, what have we studied? Let's recall real quick, right? After that, we are going to see what we are going to study today, and we are going to study that. So, pretty interesting class it is going to be. First of all, we saw what is me. In the previous class, we solved a lot of questions. Hopefully, you have tried more and more questions after that. Hopefully, I can just hope. Okay. After that, we solved. Before that, we saw a few things. Let me show you. Hello, JNV Rajkot, JNV Mahi, which is a union territory, by the way. I got to know. Okay. Outline in the previous class, we saw how G varies when we go up and down. In the previous one, before this as well, let me start from the very beginning itself. What we saw is we saw a lot of things: Newton law of gravitation, how questions are formulated on that basis, right? What is G, how to calculate G, what are the various values of G? Okay, how, if we go at a certain height, how will G vary? If I'm going down the earth, how will G vary? These things we saw, right? Then we saw what is gravitational field strength, right? Today we are going to see, let's get back to today. Today we are going to see what is gravitational potential. You might say, sir, it's pretty simple. I have already learned MGH. Let's see if it is true or not. Okay. If it is true, when it is true, right? Okay. Then we are going to see potential due to various bodies. For example, point mass, for example, solid sphere, thin spherical shell, and a ring. And we are going to sum up this class after that. Not a very big class, but very important class that I can say, right? So let's begin with what is gravitational potential. And before that, why do we need gravitational potential? Why we need gravitational potential, which I'm going to, symbolize with the V, right? Very big. Okay, which I'm going to symbolize using V, right? Let me just, this is not looking good. Yeah, with the V. Okay, so see, why do we need V? First of all, we saw force, right? What is force due to gravity? We saw G m1 m2 by r square. This force is between two bodies of mass m1 and m2 when they are r distance apart, right? Then we saw what is gravitational potential G m1 by r square. This gravitational potential was due to a specific body. For example, this is only due to mass m1 on some test mass m0, right? So one thing about these two are, these two, both of them are vector quantities, right? And we saw adding or subtracting or, dealing with vector quantities, according to me, is a very painful thing to do, because you have to calculate the magnitude, you have to see what is its direction, etc. Right? But gravitational potential is a scalar quantity. JNV Rajkot is going out and coming in. Why is this JNV Rajkot? Okay, let's see. I'll just give you a quick recap what I have said till now. Gravitational potential, why do we need that? That's what I'm saying. Okay, since force and what do you say? Force and gravitational field are vector quantities, they are very hard to deal with, right? So what I'm going to do is what physicists in the 250 years ago did was they introduced a scalar quantity, right, which is called gravitational potential. Because scalar quantity is easy to deal with, we first calculate it, after that we convert it into gravitational field and potential. So since V is easy to deal with, we calculate V, and then what we are going to do, we are going to convert it into gravitational potential and gravitational force. As simple as that. Hopefully this is clear, right? What is the use of this gravitational potential? To make our life a little more easier. You might think, sir, you're including one more thing in the class. Okay, you're increasing our syllabus, sir, and you're saying ki, it will make your life easier. So that is the case. Okay, it will make your life easier. We are going to solve questions and you'll know about that. Okay, So I hope this is clear. Why do we need V? Now we are going to see how to calculate V, right? That's the most basic question. Okay, we finally got what is V. Now we are going to see how to calculate V. So first of all, if this, let's say in this photo, if this stone is of mass m is at height h, so what we are going to do? What is the potential energy of this? You'll simply say, sir, the potential energy, which I'll denote with, let's say, U, will be given as mgh, as simple as that. But now this is of class 9th thing. We are going to increase, obviously. We are going to, learn more things. So, acha, by the way, gravitational potential and potential energy are two different things. So first we are going to talk about potential and then we are going to see. So if you want to write down gravitational potential, the definition is it is a scalar mathematical concept using which we can calculate physical quantities like gravitational field, force, potential energy, etc. This is important. Okay, this is important. Write it down. It will be helpful. Write it down. V is U. It is a mathematical concept. Okay, scalar mathematical concept. It is a pure mathematical concept. It does not have any physical representation. Okay. Let's see. Potential due to a point mass. What is potential due to a point mass? Let's say this is a point mass m. What is point mass? I already told you. Whose mass means is concentrated on a small point, or I can say the distance which at which I'm measuring is very much greater than its dimension, right? So I'm interested in calculating potential due to point mass at this point P, let's say. How to calculate it? Now, so potential, first of all, I'm going to say potential is a depends on potential depends on two reference point. Okay, one thing is you can't directly say depends on reference point. Let's say just reference point. Okay, first of all, you can't directly say ki, okay, potential at a point, what is potential at a point, calculate. You can't say that. What you can say is then ki, what is the potential difference with respect to some reference point. For example, if I take an example of previous this one, okay. So what is the potential energy of this stone? It is mgh, right? So you're measuring the height from this point, right? See, from this point you're measuring the height. What if I said the land is here, or consider the land from the underground? The potential will change, right? That will be a new height, let's say h dash. Potential has changed, right? It depends on the reference point you are taking. Exactly. Do you get my point now or not? The potential depends on a reference point, which is very important. So what to do, sir, now? So what I'm going to do is I'm taking a reference point Q here. All right. What I'm going to do is I'm going to take one mass. Let's say this is my mass. Okay. This is my mass. What I'm going to do is I'm going to bring this mass from this point to this point, right? I'm going to take this, bring this from here to here. Okay. What if I just left this mass here at point Q? So this our mass, original mass, is going to attract it, right? Imagine everything is in space. Okay. Our original mass is here. If you can see me, our original mass is here. And if I take another mass and leave it there in space, what will happen if this mass is very massive? Okay, compared to our test mass, it will just, that massive mass will attract it towards here, right? As simple as that. So this mass is going to be attracted. Is this clear, guys? This mass, if we keep at point Q, it will automatically get attract and be here. Now, what I'm interested is in, at this point, I'm going to, pause everything. Let's say there was a video going on. It started from point Q. It came. And at this point, I just paused the video. Okay. At this point, can you say what is the distance? Let's say the distance is x. We don't know the distance yet, right? Let's say at this point the distance is x. Okay, and at a very microsecond, okay, at a very microsecond, this moved a distance of, let's say, dx. At a very small time, it moved dx, right? Now, what I'm going, is this clear till this point? Is everything clear? I hope everything is clear at this point, till this point, right? Now, what we have to calculate potential, right? What I'm going to calculate is first work done. Okay, work done. Since one force is acting on it in this direction, what is the work done by this force? Let us calculate that. So chota sa work done will be force into chota sa displacement dx. Yes or no? What is the value of force? What is the value of force? G capital M and iska, let's say, small m, test mass m naught, let's say, by what is the distance? X square, right? Just substitute it here. What will be the value of dw? Dw will be equal to g m m naught by x square into dx, right? Now, this is dw, means chota sa, means very small work done. If I want to calculate total work done, what I have to do? I have to integrate it, right? So I have to integrate on both sides. What will be the limit of integration? The limit of integration will be from where we are, for work done, it will be 0 to total work done. Initially, it was 0 work done, let's say. Finally, it was total work done. Now, here, what will be the limit? Since the variable are dx and x, the variable is x, right? So x, it is initially, it is, let's say, at this point was, let's say, L distance away. So initially it was L, finally it became R, right? From here to here, L to R. So what will be the value? Substitute it here. Let me just highlight this so that you won't get confused. Now, work done, this becomes work done, right? That will be equal to Gm m naught by x to the power minus 2 dx L to R. L to R. Okay. So what will happen? Calculate it for the g m m naught x to the power minus 2. After integration, it will give x to the power minus 1 divided by minus 1, right? What is the formula for integration? X to the power n dx integration is equal to x to the power n plus 1 upon n plus 1 plus c. Since limit are given, so I'm just taking it like this. So this will come out to be g m m naught by x minus g m m naught by x. Acha, substitute, sorry, I have to substitute the limits, right? L to R. So just substitute the limits. What will we get? 1 by R minus 1 by L. As simple as that. So this is our value. So this is our work done, right? This came out to be work done. What is work done? Minus G M M naught bracket 1 by R minus 1 by L. As simple as that. This is the work done we calculated. Okay. Now, we calculated work done, right? Physicists defined this potential, this scalar quantity as, let me just color it really fast. Okay. Physicists defined this potential as, yeah, they defined this potential as work done by unit mass. Work done by unit mass, this is defined by physicists. So what will be the potential in this case? G m m naught by 1 by R minus 1 by L divided by m naught. So m naught and m naught will get cancelled out. And what is this V? V is from, can I say V is from Q to P, right? So can I say this is change in potential from Q to P, right? This is change in potential from Q to P. Now, we don't know the value of potential. We want to calculate the value of potential at point P, as you can see. But we don't know the value of potential at point Q as well. So what I'm going to assume is, I'm going to take an assumption. Yes, in physics, nothing is, complete without assumption. Okay. Assuming, this is important, by the way, guys. Let me write it with a proper, yeah. Assuming, what do you say? Assuming Q is taken on infinity, and at infinity vq is equals to 0. Means I'm saying ki if I go far away, very, very far away from this mass m, okay, infinitely far away, will this mass m affect me? It won't, right? If I'm going very, very far away from a mass m, it won't affect me, right? So potential or electric field or sorry, gravitational field or force due to everything will become zero. So that's what I'm assuming here. Ki assuming q is taken on infinity. Okay, q point is taken on infinity. That will mean ki VQ is 0. So can I write it like this? Let me erase this. Can I write it like this, guys? Key delta V of P minus, sorry, not delta, V of P. Can I write it? V of P minus V of Q, change in potential is equals to minus G, sorry, minus GM, just a sec, minus gm bracket 1 by r minus 1 by l. If I'm placing that point at infinity, placing that point q at infinity, so distance from m will become infinity. So this value of l will become infinity, right? So I'll just place l as infinity here. What will I get? This term will become 0, right? When l tends to infinity, vq tends to 0, not infinity, 0, right? So VQ became 0 is equals to minus GM by R. This is very important. This is very important. Okay. Hopefully this is clear to you all. Hopefully this is clear. JNV Mahe, is that clear? Can you guys tell me? Is this clear? How did we calculate potential at a particular point? If someone asks calculate potential at a particular point, what you have to think first in my mind, ki we can't calculate potential at a particular point. If we have to calculate potential at a particular point, that means we have to take the other point as infinity. Okay, JNV Mahid. I really like the name Mahid. Okay. Okay. So this is the question. I'm giving you guys 2 minutes to solve this question, right? You can calculate, there are three masses m, m and m at point a, b and c respectively. What you have to do at point o, you have to calculate the gravitational potential and field strength at point o. Come on guys, calculate it. I'm giving you 2 minutes. Your 2 minutes starts now. Come on guys, try to do it. Okay, people have been, talking in YouTube chat as well. So hi to everybody. Okay. So 1 minute I think is over. Yeah. 1 more minute. Come on, guys. Try to do it. By the way, today is Swami Vivekanand ji's birthday. So happy birthday to him. Great guy. Okay. Let me solve this question. No? Time's up. Let me solve this question. Pretty simple question, I would say. Uh, let me just take, yeah, let me just enlarge this pic. All right. Yeah. Okay, I can't enlarge it. Fine, no issues. I'm going to draw it again then. So let's say this is a square. Why is it becoming trapezium all of a sudden? Because I chose trapezium. Very good. Okay, let's say this is a square and there are three masses kept at these three corners, right? Now we have to calculate. Let's calculate field first. Okay, we calculated field in the previous classes as well. Let's calculate field first. Then you'll get to know how much easier it is to calculate potential. All right, deal. Now let's go. So field due to, let's say, this guy will be in this direction. Field due to this mass will be in this direction. Field due to this mass will be in this direction. Let's name them. The name are 1, 2, and 3. Field due to 1 will be equal to m. Gm by, what do you say? Mass is m, right? So let's say masses are m. And what is the distance between them? A. So Gm by a square. In what direction it is? Let's say it is in x direction, negative x direction. E2. That will be given as Gm by, in what direction it is? It is in y as well as x direction. So what is the distance between these two? So this diagonal will be equal to root 2a. So root 2a whole square. Into what is the minus I plus j? Direction C. X में minus I, y में plus j. Okay. E3. Gm by, what do you say? A square in j direction. So what is the total? Total will be equal to, simply add them, right? This is in vector form. Simply add them. Gm by a square will get common. Here you are remained with minus I. See, in this only minus I remains. Here minus I plus j and plus j here. Can you tell me one thing I have missed? Can you guys point out what I have missed? Can anyone tell me what I have missed? Okay. Should I tell? Chalo, I'll tell you. See, Gm by a square we have taken common. Na? Here root 2 square is remaining. So root 2 ka square is 2. That was, missing. Gm by a square minus I by 2. That will be minus 3I by 2. Plus, this will be plus j by 2 plus j. That will be plus 3j by 2. Hopefully this is clear. So E vector will be equal to 3 by 2 becomes common, Gm by a square into minus I plus j. Hopefully this is clear to you all, right? If I want to, calculate the magnitude, it will be 3 by 2 Gm a square into root 2. See, I ka square plus j ka square, that will be root 2 under root mein. So this will give out to be 3 root 2 divided by 2 Gm by a square. This is our electric field magnitude, right? Quite pain to, calculate, right? Quite pain to calculate. Vector, you have to think of vectors, you have to, see the direction where it is, etc., etc. Now, let me calculate. See, a very small space in the screen is remaining, right? I'm going to calculate whole potential in this space only, right? So what is potential? What is total potential? That will be simply equal to, V will be simply equal to V of A, okay, V of first mass, let's say, not A, potential of first mass plus potential of second mass plus potential of third mass. As simple as that. So what is the potential, formula of potential we just calculated? That is minus Gm by R. So first, G minus gm is small m and r is distance a, right? For first one, so that will be equal to minus gm by a. For second, the distance is root 2a, so that will be equal to minus gm by root 2a. And for third, it will be equal to minus gm by a. So minus gm by a becomes common. Here you are remaining with minus 1 by root 2 and minus 1. So that will be equal to, if I solve this equation, what am I left with? I'm left with minus, let me just solve it, minus 2 minus 1 by root 2. See, I solved it in the space itself. Now using this potential, physicists are so smart now. Using this potential, we can calculate a gravitational field, you can calculate force, etc. So I think this is pretty good leap in physics, right? Pretty good concept to invoke. Is that clear to everyone? Hopefully this is clear to everyone, right? Okay. Now I'm going to give potential of various objects, but I'm not going to I'm not going to dig deep into the derivation part. I'm just going to give what you need, right? Why is that? Because in class 12th, you're going to learn the same things in a much detailed fashion. For example, this is our, let's imagine a solid sphere. Okay. Let me color it then. This is a solid sphere, let's say. Just a sec. This is a solid sphere. Okay, it is filled within, by the way. If you can't tell by my coloring. Okay, it is filled within like this. Yeah. JNV Mahe, are you guys listening? Some of you might be sleeping. I'm getting a feeling as a I'm getting a feeling from inside. Some of you guys are sleeping. Is that the case though? Okay. Let's say this is R. Let's say this is a solid sphere. It is R, as simple as that. And okay, we have to calculate potential on 3 points. One is outside, one is on the surface, and one is inside, right? On 3 points. One is outside point, inside on surface point, and inside. So I'm going to give you direct formula. For outside, this guy acts as a point mass. For outside, this whole solid sphere or any type of sphere acts as a point mass. So I'm going to write it down. For outside point, write it down with me. Sphere acts as a point mass. For outside point, sphere acts as a point mass. This is very important. Okay, this is very important. You have to, keep in mind. Important. I'll just underline it. Okay, let's move on. If it acts as a point mass, so V outside will be equal to minus gm. This is the mass of the whole total by what is the distance between, let's say, in general, R. Now, V on surface. For surface, what we have to do, we have to substitute this as this distance as capital R. See, this distance is capital R, right? So we have to substitute R with capital R. Now, V on, what do you say, inside? This is important. V on inside is important. Gm by, see, it is very same. Gm by, Gm is common. Now what you have to do, you have to take R cube here. All right. If you take R cube here, you have to introduce the R square in the denominator. What will that be? That will be 3 by 2 R square minus 1 by 2 small r square. Remember this. This is very, very, very important. Okay. For a solid sphere, this is. For a solid sphere. Here, I'm underlining the solid sphere part. These you have to remember. Okay. Just remember these. Just note it down. Note it down, everyone. Note it down, guys. Note it down, then we'll move on to next thing. Note it down first. This one is important. I'll just mark important here. Yeah, It looks like a gift ribbon though. Okay. So what does the graph of this look like? So outside, if you can see, V is outside. Outside V is inversely proportional to. At surface, it has some maximum value, right? Not maximum value, but some value which is constant. I'll just write it down as constant. I'll just write it down as constant. And inside, it is kind of a quadratic type equation. See, this is a quadratic equation. So quadratic. And we know by quadratic equation, acha, if it is inversely proportional to R, what type of graph will you get? Let's just plot this graph. Okay. Okay. This is not what I wanted. Yeah. Let's say at this point, blue color. At this point, you have R equals to R. At this point, you have R equals to R. Now, after this means outside point, what am I getting? I'm getting a like this, right? V is inversely proportional to R, right? So the graph will go down like this. Now, on surface, it has a value. On surface, it has a value called that value is Gm by R, right? Now, minus Gm by R. Let's say we are taking negative potential up. Okay. Okay. What about inside? How is inside going to look like? How do you think inside is going to look like? Can anyone tell me? Can anyone tell me? Think of it. Try to draw it in your graph. Try to draw it. Don't tell me. Just try to draw it in your graph. Okay. Okay, my turn. Since it is a quadratic equation, I think it will become a parabola at some point. Yes or no? Since, see, the variable r is negative. If you can see here, the variable r is negative here. The parabola will be facing downwards, right? You have studied this in, I guess, class 10th. If the variable is negative, the parabola will be facing downwards. So it will become something like this, right? A parabola. Let me just draw it more nicely. A parabola like this, right? Hopefully this is clear. Is this clear, guys? Is this clear? Is this graph clear? In this axis, we have plotted potential. In this axis, we have plotted R. So note it down. Note this graph down. Note this graph down. And one more thing, if someone makes a graph on the other side as well, that is wrong. Okay, that is wrong. There won't be any graph on this side. Why is that? Because the value of R, what is R? The distance from the point, let's say point A to center, or point B to center, or point C to center. What is the minimum value of this R? The minimum value of this R can be 0. If you reverse that value, right, it will again be positive, right? So minimum value is 0. R cannot be negative. यहाँ पे मैं लिख देता हूँ, R cannot be negative, right? Remember that. This is important. So hopefully this graph is clear to you all. Now let's solve a question. At what distance d from the surface of a solid sphere, at what distance d from the surface of a solid sphere of radius r, potential is same as at a distance r by 2 from the center? Means I'm going to make a sphere here. There is a sphere. Okay, this is our sphere. For example, at r by 2 distance, from center to r by 2 distance, this is r by 2 distance, right? There will be certain potential, let's say v r by 2. So at what another distance, okay, from this center, let's say that distance is, let's say r. This potential will be equal to r by 2, right? And you know this potential should lie outside, right? So for inside, v inside r by 2 should be equal to v outside r by 2, right? So v inside r by 2, inside the formula of r by 2 is minus gm by r cube 3 by 2 r square minus 1 by 2 small r square is equals to V outside Gm by small r. Hopefully this is clear. Now some things might cancel out, minus minus and minus gm will get cancelled out. The value of r is small r is the value of small r for this guy is r by 2. The value of small r this we have to calculate, right? Just substitute it here. So what will we get? We'll get 1 by r cube bracket 3 by 2. Acha, can I take this 2 outside? I'll just take 2 outside, right? Okay. 3 r square minus what is r square by 4 is equals to 1 by r. So let's solve. So 4 3 is a 12, 11. 11 r square by 4 into 1 by 2 r cube is equals to 1 by r. So value of r will come out to be 4 into 2 r cube divided by 11 r square. So that will be equal to 8 r by 11. So at distance 8 r by 11, the potential will be equal to at the distance r by 2. Hopefully this is clear. Let's see in the graph if this makes any sense. Okay, let's see in the graph it makes any sense. So at distance r by 2, let's say this distance r by 2, where can I find this value r by 2? Okay, you have to, okay, I'll give you a homework. Since the time is running out, I'll give you a homework. You have to figure out ki, how does it make sense in the graph? Okay. Till then, I'm just going to tell you one last thing. Then we are going to wrap up this session. Okay. Potential due to a hollow sphere. It is simpler than the previous one. Okay. This is, let's say, a hollow sphere. This is a hollow one, right? Okay. Of radius, let's say, capital R yet again. Now, V outside, since it is a sphere, it will act as a, what do you say, Gm by R means it will act as a point object. V on surface, it's pretty simple. R ki jagah, you have to substitute capital R. V out, sorry, inside, it is a little tricky. Okay. For this case, V on surface, for this case inside, it is equal to the surface one. Means V inside is equals to surface. Let me just write it down. Inside a hollow sphere, potential is constant. What did I say? Potential is constant and equal to potential in the, and is equal to the potential on the surface, not in the surface, but on the surface. On the surface. Just write it down. This is very important. Okay. Inside the potential is this. Acha, now you might also think yeah, question will become easier. So what will be the graph look like of this? Let us just draw this graph and we'll just wrap up this session. Okay. What will the graph look like? Okay, wrong. Okay, again wrong. Okay, what should I do? Okay, now I think it's right. Yeah. So let's say this is what do you say? This is our line which represents r equals to r. This represents r equal to r. At this x-axis, I'm going plotting r. At y-axis, I'm going plotting potential, right? So outside, yet again, we can see potential is inversely proportional to r. At surface, it is constant, and at inside also it is constant, right? So outside, it will be something like this. At surface, it becomes constant. At surface, it becomes constant like this. and the constant is what will be the value of this constant? Minus g m by capital R. And inside also it is same, right? So I'm going to draw the graph like this. Inside it is same at surface. So this is the graph for potential due to hollow sphere. Hopefully this is clear. In the next class, we are going to see potential due to a uniform ring at some point, etc. Okay. After that, we are going to see relation and all. Now, let's recall what we studied today. Very simple things. First of all, what is gravitational potential, right? Acha, you might think, sir, MGH, you didn't specify anything about MGH or talked about. I was supposed to, but time is ending. What can we do, right? We'll do that. We'll do that in the future class. Now, what is gravitational potential? It is a scalar mathematical concept using which we can calculate physical quantities like gravitational field, force, potential energy, etc. Okay. One more important thing I told about gravitational potential is that it depends on a reference point. It depends on a reference. Okay, my handwriting has become horrible, so I'll just write it a little more cleanly. It depends on a reference point, right? It depends on a reference point. Then we calculate. Acha, I already wrote that here. Come on. Then we calculated this potential. And what is potential defined as? Potential is defined as work done from moving from one point to another divided by unit mass. This is important, right? This is what the definition of potential is. And we also saw we cannot calculate potential due to one point. We have to calculate the potential difference at any point. So how to calculate potential at one point? We take the other point as infinity, because at infinity potential is zero. Then we solved this question. We also saw electric field. Solving electric field is like pain, but solving potential was pretty simpler, right? After that, we saw potential due to a solid sphere. Outside, it acts as a point mass. But okay, so minus g m by r. For outside, minus g m by r, as simple as that. For inside, what have we have to, on surface, we have to just substitute small r as capital R. Inside was what do you say, important. You have to remember this formula, right? The graph looks something like this. After that, we solved a few questions, and the second part of this question is, by the way, homework. Field strength is same as the distance r/4 from the center. Okay, you have to solve this question as a homework. Then we saw a potential, a potential due to a hollow sphere. Outside it yet again acts as a, what do you say, point mass, right? Inside, on surface, we have to substitute small r as capital R, same. But inside, potential is same as on the surface. Only for hollow sphere, you have to remember this fact. Only for hollow sphere it is true. Okay, only for hollow sphere. Then we saw its graph, and we are ending this, what do you say, class. So does anyone has any question regarding anything? Can let me know. I'm giving you 2 minutes to ask me any questions. Come on, guys, go ahead. You can write it down in the chat if you want. Just ask anything you want. Free hand. Okay, someone has asked something. What is the word after potential in the first line? Okay, what first line? I have to see. What first line are you talking about? I think you're talking about the definition. So let me get the question once again. What is the word of after potential in the first line? What is the word after potential in the first line? Where is the first line? Okay, wrong, wrong place. Sphere. If you're talking about this, then this is sphere. All right, I think that was it. Okay, so no questions, I'm assuming. Okay, guys. So hope enjoy your day, remaining day. Keep learning, keep